Welcome back once again. This is part 3 of my talk. So in part 3 we're going to talk about the associative and co-associative cases. In fact, I'm not going to go through the details of the co-associative because it's virtually identical to the associative case. So let's set it up. So let's let M7 be a manifold with a G2 structure. Remember, that means that there's a Riemannian metric, there's a special kind of 3 form, and there's a special kind of 4 form, which is the Hodge star of the 3 form, because this manifold is also oriented. So from these structures, by raising an index with the metric using the musical isomorphism, we in fact get two other special kinds of operations. First is a cross product, and this is defined by the cross product of two tangent vectors u and v. If I take their inner product with another tangent vector w, that's phi of uvw. And there's another operation which is a vector valued 3 form chi, which is obtained in the same way using psi. So this vector valued 3 form applied to u, v, and w, when I take the inner product with y, that's the same as plugging in those 4 vectors into psi. So for those of you who know about vector cross products, the theory of vector cross products of Brown and Gray, this one is a vector cross product, the 3 form, just like an almost complex structure, an orthogonal almost complex structure is a vector cross product. This one is not a vector cross product, but that doesn't matter. It's still giving us a calibration. That's just an aside. Okay, so we have these structures, and again, we do not assume that either one of these is closed. They're both calibrations in the sense that they both have comass 1. If they're both closed, we have what's called a torsion-free G2 structure, and those have special holonomy. The holonomy of the Levi-Civita connection lies inside the exceptional Lie group G2. But if one of these forms or both are not closed, then that's not true. Okay, and remember that these submanifolds are minimal if the associated calibration form is closed. We're not assuming that, but it doesn't matter. We're not going to use any properties of minimality. Okay, now this is what we're going to do. Let's go through the associative case in detail. We're going to vary the 3 form in the space of 3 forms by varying in the direction of exact 3 forms. So beta t will be some family, one parameter family of 2 forms, such that at time 0 we get 0, so that phi t at time 0 is phi. And let's call beta dot the velocity of beta t at time 0. Okay, so for those of you who know about G2 structures, if I take a G2 structure, this special kind of 3 form, and I move it a little bit, it's still going to be a G2 structure. The space of G2 structures is open in the space of all 3 forms. So for sufficiently small time, this path phi t will still be a G2 structure, and therefore it will induce a Riemannian metric. It's a fact that any G2 structure induces a Riemannian metric in a very complicated, very nonlinear way. Okay? So let's look at the class of metric variations upstairs that are obtained by varying the 3 form in the direction of exact 3 forms for small time, and that gives us a family of Riemannian metrics upstairs. Here's an aside. It's not going to really be important so much because I'm not going to show you the full details of the calculation, but just to get a sense, at least to first order, the infinitesimal dependence of the metric on the 3 form is obtained as follows. So if I have a 3 form which is varying in the direction of some 3 form eta, which in our case is going to be d beta, but let's just say we have a variation of a 3 form eta, then you can construct a 2 tensor by contracting eta with phi on 2 indices, 2 pairs of indices. That leaves us with 1 pair of indices, so that's a covariant 2 tensor on M. And then the first variation of the metric is going to be a symmetric 2 tensor H, where this H is basically obtained from eta hat by taking the symmetric part with some factor and throwing away some multiple of the trace. Not the full trace. Eta still has a trace. This is not trace-free. This is going to be very important later. This is not trace-free in general. Okay, but we do have to adjust this thing, eta hat, by some multiple of the trace. Okay, so that's how the metric will change. here's our theorem A. Suppose we have a submanifold, oriented three-dimensional submanifold, which is calibrated with respect to phi. That means it's associative. And suppose that we have a family of metric variations upstairs that are induced in this way by varying the three form in the direction of exact three forms. Then the metric G is critical for the volume functional. Okay, that's exactly the theorem A in this case. Again, here's a sketch proof. Since it's associative, there's a special kind of adapted orthonormal frame for the tangent bundle along L. We can find a local orthonormal frame for M such that the first three are tangent, the last four are normal, and they're of this special type. E1 cross E2 is E3, and then E5, E6, and E7 can be deduced using the cross product from E4 and E1 and E2. Okay, this is a special kind of G2 adapted frame. And using this frame, you can compute that the first variation of the volume functional at time 0 turns out to be exactly the integral over L of eta. Remember, eta was phi dot at time 0. Okay? And this is quite an involved calculation. There's some miraculous cancellation that happens that makes this happen. And the reason I want to emphasize it is because when we get to the spin 7 case, something very interesting is going to happen, and I'm going to come back to this, that there's some really miraculous cancellations that's making this work out exactly right. And since eta is d beta dot, we have something exact, and therefore we get something 0 by Stokes' theorem, because L is compact without boundary. Okay, so I'm hiding all the hard work in here. Okay. So in the second part of my video, when I was talking about the UM structure, a lot of our results were generalizations of the work of Arezzo and Son. Right? The rest of the talk, the G2 associative, co-associative, spin 7 Cayley case, these are all new. Okay. So let's look at theorem B in the associative case. Theorem B says, suppose our metric G at time 0 was critical for all these kinds of special variations by varying the three form in the direction of exact three forms, then in fact L has to be associative. Okay, and let's go back and see how we did it in the UM case. Okay, remember this function, which is playing a big role. This function was half the distance squared to the submanifold. Okay, this is a function which has a nice properties along the submanifold. Its gradient is 0, and its Hessian is the metric in the normal directions. So in case 1, what we did was our one form that was varying was J of grad f, and J of grad f is exactly what you get when you hook grad f into omega. So an obvious idea is to make our two form time derivative at time 0 beta dot to be just hook grad f into the three form phi. That's clearly the thing to do, except that it doesn't work. Right? You calculate this, and you can't conclude that that L has to be calibrated if you take this for beta dot. Okay? So you have to work a lot harder, and it took us quite a while to figure out what the right thing to do was. Instead, we choose a family of two forms whose time derivative at time 0 looks like this. So we do plug in grad f into the three form, and then we plug in v, so we get a one form, and then we wedge that with v to get a two form, where v is any vector field on the ambient space M, which has the property that when you restrict it to L, it's purely tangent. It has no normal part. Okay? So v is arbitrary with this property. And if you take this for beta dot, then using an orthonormal frame for L with a lot of hard work, you can compute that the first variation at time 0 for this variation, this particular variation, again becomes something non-zero times a non-negative integrand, which is the sum of the squares of the norms of the normal part of V cross EA. So this is a tangent frame for L. So therefore these have to all be 0, and that means by taking V to be something which, so this is what we get is that V cross EA is tangent to L for all V that's tangent to L. Okay? So by taking V to be EA, EB, EC, we get that EA cross EB is tangent to L for all A and B, therefore L is associative. I didn't say that earlier in the talk, but that's the definition of associative, that it's closed under the cross product. The tangent spaces are preserved by the cross product. Okay? So that's theorem B in the associative case. And then the co-associative case is essentially identical. Okay? So again, we're going to vary the form, the calibration form. This time the calibration form is psi, star of phi, and we're going to vary it in the direction of exact four forms. And this time, for theorem B, what we have, so if you do this, if t is sufficiently small, this is going to be a non-degenerate four form. It's going to induce a metric, and you're going to see that if you start out co-associative, the metric is critical for such variations. And conversely, suppose the metric was critical for all these variations, you want to prove that L had to be co-associative. You do it by choosing this as our initial velocity for the three form gamma. You plug in again grad f into the four form and two vector fields, which both restrict to tangent vector fields along L and are linearly independent. So here, V and W are tangent to L and linearly independent. So this is on L, right? Because these are vector fields defined on the whole manifold, and the only thing we need is that when you restrict to L, they're both tangent to L and linearly independent. Otherwise, it's the same thing, and there's some really miraculous cancellation that happens again, because the way that the metric GT is induced from the four form psi t is highly nonlinear. Okay, so that was the G2 case. The associative case I talked about in more detail. The co-associative case is very, very similar. But the rest of the talk, I want to discuss the spin 7 case. So maybe this is a good place to take our final break, and we'll continue in part 4.